Okay, so we are learning our last section of this chapter. This is the last thing. Then we'll be done. So this is, what functions have we learned the derivatives of? We've learned
Logs, exponentials.
Exponentials, logs.
Trig
functions. We got all 6 of those, right?
And then linear.
We've learned the linear. We can take anything that's chain ruled.
Yeah.
We can take any kind of composition that is one thing over the other with the quotient rule, one thing times another with the product rule. I think there's one other type of basic function which we haven't learned yet.
Arc.
Which is the arc functions. And there's
Oh,
6 of those, just like there were 6 trig functions, and that's the end. Okay. There are other derivatives, like there are other functions whose derivatives we'd have to learn different things for, but you've never even seen those functions, and you don't need them for AP.
So I with like the arc sign, which like like sine to the -1, would you just bring the -1 down and then subtract 1, or is that not how you do it?
That's what I did.
That's what I was
That would
thinking.
explain why my numbers
Good
were so
question.
weird.
So when you have sine to the -1 of x, remember this -1 really just means the inverse function. What I'd think of it as is it's kind of, I don't like this, it's just the way that the notation has evolved over the last few hundred years. That -1 means inverse function, it's like part of the name. Don't think of it as a number you can do anything with. It's part of the name of the function, that's it.
It was one of those things that I tried clearly to confuse.
Does that make sense?
Yeah, that makes sense.
Like it's just, that's the way that the notation has evolved, and I think I learned it at some point, but I forgot. It's just the way that it like developed over the years, so. Good question, Austin. All right, let's just look at reviewing our trig, our inverse trig guys real quick. Why do they have different graphs? Why do they come up differently? So I'm gonna show you the first 3 that we're familiar with, and then we're just gonna look at our textbook real quick for the other ones. There's also some special calculator rules with this, but I'll probably do that with you tomorrow.
So we for sure have class tomorrow?
I think so.
I'm so confused
I'm not
about
for sure
this
about
entire
anything.
thing. I don't
Just
even
don't worry
know
about it.
anymore.
Just don't worry about it. I'm not worried about it.
I am.
Yes,
I found out that I have a classroom of kids, the same kids, for 45 minutes.
Yeah, I saw that.
Yeah, it's not
What was with that?
I don't know. I feel unloved.
Okay, so this is the sine. This is the cosine. And this is the tangent. These are the domain restrictions, if you remember, that you use to form those inverse functions. They look familiar, right? So the domain restriction on sine is you only take -π/2 to π/2. You include those endpoints. Cosine, we go
Pi to 2 pi, or 0 to pi, or
0 to pi.
thank you, Allison.
0 to pi.
And tangent's the same, except you can't include the endpoints. Why are those not open? Let's remember what the graph of tangent looks like.
tangent, it's every pi over
It's
2
an
goes an
asymptote.
asymptote.
Those are asymptotes, right? That's why those aren't included.
I'm kind of confused on the cosine one because it really looks like it goes past 0. Like,
You mean my picture?
Isn't that the domain? Are we talking about domain?
I'm talking about the domain that you're cutting on those guys to form the inverse function. Because if you think about it, remember, what does a sine wave look like?
Like that.
Let's just draw it.
Oh,
Sine wave
never mind.
looks like
Todd
this,
cleared
right?
it up.
Oh, yeah.
Unit circle. Okay, I was thinking actual numbers, not unit circle.
Sine wave looks like this, right?
Oh, so that's why those.
That is the sine of x. In
How
order
sine
to
of
find
x
its
is-
inverse function, it has to be 1-to-1. It doesn't pass the horizontal line test right now. It hits it an infinite number of times, right? It's going to keep hitting the wave. So that's why you have to restrict it somewhere, like this. So it's between -π/2 and π/2. That way now it does pass the horizontal line test, and it does have an inverse. And remember, how you find an inverse is you reflect. Should really look a little better. You reflect over the line y equals x. That's what an inverse is. It's where you exchange x and y values. So the inverse sine then looks like
The infinity
that.
sign.
Yeah. It's just the red. This red part is the inverse sine of x. What's another name for that? Can somebody help me? Because this will help you with the stupid -1 thing, right? You can call this the arc sine of x, and then you don't have to worry. You can see it's clearly a different function. Its purpose mainly is to undo the sine function. But can you guys tell me, is x squared and square root of x the same function?
No.
They're inverses, right? But they look totally different. They have totally different properties. They're totally different functions. Totally different functions need to have totally different derivatives. Does that make sense? Even though they have a similar name, they're not the same thing. Okay? So we could do the same thing with cosine. So let's try to draw that one. We're going between 0 and pi on this guy. Where's cosine start? Austin, can you help me?
Cosine.
Let me draw the first part of the cosine.
Oh yeah, it starts up. Yeah.
Starts up here, and then
Yeah.
I go and
Yeah.
come all the way back up, right? But I'm only going to pi, so it's going to be like all the way down. You guys following me? We know this. And it crosses like right there. So then you'd reflect that. This is really hard to draw sometimes.
Whoa. So how would that look?
Well, I'm going to try to reflect it, right? This part kind of goes like that. This part kind of goes like... I'm going to have to look at my picture. Oh, my picture's terrible.
Never mind.
Let's open our book to page 372.
Yes.
Mr. McGee, by chance, next thing we're doing is the integration rules?
No.
Oh.
We're done. The integration's not till we're in. We're
I don't know, it's just
doing
on the
rules.
next.
This is the end of rules for quite a while.
Gross. That's what it is.
Is that a
I'm
good
tired of
number?
learning rules. I want to do stuff with
Rules are right here. Looks like school. You're looking at
Okay,
the
so-
I'm like, I don't
It's not that right.
Yeah, that doesn't look
see. What have I done? It looks so messed up. How does it do?
So I'm trying to reflect this. It's kind of hard to draw. This guy, it ends up looking like this. It goes pi over 2. So it's going to go like something like that. Mine doesn't match up very good.
It's okay.
This part's supposed to be there. Then you go. So that part gets reflected that way, and that part gets reflected up that way. It's really hard to do that. It's hard to see it, you know what I mean? But anyway, it is a reflection, if you can trust me, despite my terrible drawing. And then tangent, you know, you do the same thing. Tangent's real easy to see. Watch. So tangent, we've got the asymptotes, right? Tangent's actually probably the easiest one on this. So I'm going to draw the tangent in black. There's my tangent of
It's
x.
just the other way.
If I reflect it, I think these asymptotes really just get turned this way. And it's going to look like... That should really like be crossing.
I see.
So there's my inverse tangent of x. I should really have this coming down a little bit. Below there. You get the point, I think.
Yeah.
Okay, so you could go ahead and do that with each one of the other functions too. So you guys see on 372 how they did it for arcsecant? And then they have what arc cosecant looks like, and they have what arc cotangent looks like. Okay, so we don't need to have like all these graphs memorized or anything, you know, we don't have to do that, but we just need to kind of remember how this works and how they come about from reflections, and the main idea is that they're going to have separate derivatives. Okay, let's do a couple things. You might need this for some of our problems, but I think mainly it's useful in Calc 2. You learn this technique called trigonometric substitution in Calc 2. So you need to be able to do things like this.
Is this like example
This is
one?
stuff we did last year in pre-calc. So this is a review. So I'm just going to do a bunch of these real quick.
Can you put some people?
It's up to you. I mean, if you're comfortable, they'll do it. We did do this a lot.
Will these only take one line, or is there work involved?
They're not long.
That was a prime example of a non-answer.
I don't see how.
Okay, so remember, when it says arc function, it's asking what angle has a sine of -1/2. So the best way to do that is to draw it, right? So you say, okay, what angle has a sine that's negative? Sine is the y value, so we go down. I'm looking for that angle.
Wait, so you started
Opposite. And I say, what is that angle?
30.
Oh, excuse me. Thank you. 30 degrees,
In that quadrant, negative 30 degrees.
which is negative,
6.
right? Okay. This marker. So this guy,
Or
what
lower
angle
pi
has a
over 6.
cosine of -1?
Pi.
That's over here.
cosine of negative.
The answer is pi, because that point is that. Cool. What angle has a tangent of √3? Tangents in these two quadrants, which one's going to be positive? Tangent is opposite over adjacent. What angle is that? 60, so pi over 3. We did all this stuff, right? I think you might need this on a couple of your problems. That's why we're doing it. Okay, and this kind of stuff you really need in trig substitution later on, so I thought we'd just look at it again.
Oh, this is on the or stuff like this is on the ACT occasion.
The SAT or the
ACT, it was on the second one.
Yeah. Okay, so sine of the arc secant of x. If you've got a composition like this and there's variables, do what you did over there. Just draw your reference triangle again, okay? So I'm going to draw my reference triangle. Okay, so this inside part, I'm going to focus on it. Okay, so let's just look at this inside one. It says, what angle has a secant equal to x, right? Just don't even look at that other part, just cover it up. What angle has a secant equal to x? So let's call this an angle. Let's make it secant x. Secant is cosine, right? It goes with cosine. So cosine would be here over that. So
you
which
have
one of
x
these
over
things is
something.
x?
No, x over 1.
X over 1.
Right?
Wouldn't we go like that?
Oh, for, yeah.
Am I right?
Yeah.
Yeah.
Oh,
If if that said arc cosine of x, we'd put x and 1 here.
So in that side is x squared minus 1.
Wait,
So
so
then you
wait.
Sure. So how we come up with this? We're saying if we look at secant of theta, the secant of theta is what if we read it off? So that means that this and this are the inverses. Okay? So now you said, Caitlin, you were going to go and fill this in. So you use the Pythagorean theorem and you go, okay, a squared plus b squared equals c squared. You fill that in. So c squared equals thing squared plus 1 squared. So that means thing squared equals x squared minus 1. So this is the square root of x squared minus 1. We can all do the Pythagorean theorem. Don't get lost on that part. Do it however you like. Okay.
Equals whatever a.
So then sine is square root of x squared minus 1 over x.
Okay, so this is the sine of this triangle. The reference triangle is done. This is another way to say, didn't we say arc secant of x is equal to theta? So just read the sine off that triangle. What is it?
Did we do this last
Over
year? It's pretty familiar.
X. Yeah, we did.
So you don't have to do like the product or anything like that?
No, I'm not doing any derivatives yet. This is warm up. I'm just saying you might need this.
What would arc cosine be?
It would have been something very similar to that.
It
Do
would
this
have
one.
been
Try
x
this.
over-
Try this. I'm gonna give you a few minutes. Try that out. I'm going faster than I did in pre-calc. Yes.
I don't understand.
If you want a more thorough explanation, you could go find this video for pre-calc.
No, I just don't understand the arc secant.
We're gonna go through that one together. Hold on.
Because it's secant of x.
I forgot to give you some.
Okay.
I'll do another one of those for you in a sec if you want.
I know, but then arc, wouldn't that make it different?
I guess, yeah. Because that's what it seems like.
Okay, but Mr. McGee, like, because wouldn't just sine of secant of x be 1 over x? But wouldn't the arc change it? Or x over 1? Like, if the arc was not in that problem, if it just says secant of x, wouldn't it be x over 1?
I don't know if that problem would make sense if the arc wasn't in there. Is that sine of secant of x you're telling me?
Yeah. Like, what
Yeah.
would that be?
You couldn't
Because
really.
secant is still x over 1.
Secant of
right?
x is unknown.
Yeah, so you
It is?
can't
Because it's
solve
1 over.
Secant of x is something I don't know.
But wouldn't
So
it
it's
be?
sine of something I don't know, which is I don't know. This problem's different because it says
arc secant.
arc secant.
Well,
It
I thought
says
the arc
the
was-
sine of, and you need to realize that whenever an arc function's in there, that's the sine of some angle. So if you know the sine of an angle, it's just opposite over hypotenuse, right? So the only question is, what is that angle? And that's where you have to start writing down the triangle. So you say, okay, this is some angle, so I draw a triangle, okay?
Then when you apply secant.
So then I say, that angle has to have a secant. When you write this down, let's write it down like this, secant inverse of x. That says some angle theta has a secant equal to x. So I draw the angle theta, and I make its secant equal to x by going, okay, x and 1 there. That angle has a secant equal to x. Do you agree with me?
Yeah.
So then I say, okay, I'm just going to finish that triangle off. Nothing fancy, just finish it off, do the Pythagorean theorem. You can do that yourself, and you're going to get x squared. We got x squared minus 1, right? It's the Pythagorean theorem. So just Pythagorean theorem. And then you say, okay, go back to the original problem and start over. If this is sine of some angle, and that's the angle, then it's just sine of that triangle. The idea here is that you can use this triangle to substitute in and change a trigonometry problem into an algebra basic functions problem, and that's something that's really valuable. We're not going to do a lot of it this year, but it is something that you'd use in Calc 2 heavily. And we may see a couple problems where you use something like that. It is, like those are conceptual, deep problems, it is. So if you're having trouble with it, fine. I'll do another example in a second, but let's do our derivatives. Okay, what do we get here? This, I think, is...
2.
Yeah. You can just do the inverse operation. Take the tangent of both sides. To get rid of that, forget max. I'm using too many colors here.
Yeah, a little bit.
So you get 2x minus 3 equals, you use the figure out tangent of 45 degrees, which is 1. And you get 2x equals 4 or x equals 2. So that was pretty easy. That other one was much more conceptual. Okay, so I'll do another problem like that in a second. I'll explain it over again, because it is deep. Let's learn our rules though. So if you've got that page, flip to that page so you can record these rules, and I'll probably only have time for like 2 or 3 examples.
How many more are there?
This is the last. And when we do integration rules, there's only a couple that are a little different, and most of them are like the same thing
Okay, I
backwards.
think I barely have enough room then.
Yeah, my derivatives page is almost.
It's always in the front of your book too.
What?
Yeah.
Well, it's
So if you guys looked in the front of your book, it has all of your derivatives and integrals on the very first page. And it has extra ones. We aren't going to learn all of those.
Thank goodness. Yeah.
There are some extra derivatives. I think there's about 12 or something extras. I don't remember. Okay, so Just like you guys anticipated, when we learned our trigonometry ones, the 6 trig ones, there were patterns to remember them, right? Guess what? These work like almost the same way. They have the same, similar kinds of patterns between them, so you can remember it pretty easy. So the derivative of the arc sine of x, or sine inverse of x, same thing, right? I like to write it that way because I know it's a different function. So what is the derivative of the arc sine? There you go.
Oh. That would have made my life so much easier last night when I was doing the homework.
Did you start it already?
Yeah.
Good.
I thought I finished it, but I didn't, apparently.
Okay, so sine and cosine usually went together, right? So I think if you remember arc sine, arc cosine should be no problem. Arc cosine is exactly the same.
Except it's 1 plus x squared.
Good guess.
Negative
Just
1
negate the whole
over
thing.
square root of.
Yep. The only difference is it's negative. So that's really only one thing to remember.
But if you.
Notice when you took the derivative of sine, was it positive or negative?
Positive.
Positive cosine. When you take the derivative of cosine, is
Negative.
negative. This works the same way. Okay. When you take the derivative of tangent, I guess we'll do that one next. And then we'll put cotangent with it.
Just tangent or arc?
Arc.
Okay.
Haha. Didn't have to race. Which one of those do you guys think is positive?
Tangent.
Yep. And it's probably one of the most common ones that they'll definitely put all over the AP exam. Of all derivatives, I would say that's probably one of the most common ones. Because it's used for a lot
So
of
then
things.
is the next one.
Easy.
Is that it?
Well,
For those
Okay.
rules, for
Cosine
the not like notes,
still,
just for
right?
those rules.
still got 2 more trig functions, right? Which one of the other 2 was positive?
Secant.
Secant, wasn't it? Inverse secant, right? So this guy's kind of funny. It's almost like these. You got to be real careful not to mix this kind of one up with this one. This has an x outside too, and it's backwards. I think it's minus. Yeah, just making sure. Okay, so notice sine is 1 minus x squared. This guy is a little bit backwards. We got to be careful on that. That's easy to mess up till you practice a bunch, I think. But the other one is going to be just about the same. Just negative. And we're done. That's all of our derivative rules we have this year. So I thought we'd try a couple examples. And the nice thing is when we learn those other rules, yeah, there are some other rules when we do integration. Most of them are just this backwards. Like there's some other little things we gotta like be careful with, but they're not really all new. They're all like these backwards, so not gonna be a big deal. The real question is what can we do with all this stuff?
Yes, that's. It's like, when do you use derivatives in real life? Like, I know you do because you told us,
Well,
but I forgot.
mean, people have boring relatives to learn,
I missed that one.
This is a real life example. They're for your genes.
but you gotta learn the alphabet before you can use it. I suppose. Okay, so you guys help me with this one? Let's take the derivative f prime. I don't know why I wrote it backwards. Who knows? Okay, so I think we're gonna want to go arc sine. We go 1 over square root. Now is this one x squared minus 1 or the other way? It's 1 minus thing squared, right? We got a chain rule. So 1 minus the thing squared.
Times 2.
Chain rule. We okay? That's f prime g, g prime.
So then just equals 2 over that?
Yeah, 2 over that. Let's simplify that in there a little bit. What is that? 1 minus
4x squared.
4x squared. So now a lot of people make a mistake here and have 1 minus 2x squared. You gotta square that 2 as well. Okay, careful. And let's try.
Don't you like when you're like I don't want to say dull, but it's like blurry? Like it makes the lines like a small percentage. I know why you should use these right now.
Oh, we can just get this done today. You guys have tomorrow morning. Have some questions. Where did it go on good?
So, is it 1 over 2x squared plus 1 squared?
Squared plus 1
Yep, Cassidy. And then
times
you're missing one little thing.
Times 4x?
Yeah, times
plus 1.
times
Plus
4x.
1 up above.
Times 4.
And you've got a plus 1 here, right?
Where did the plus ones come from?
It's x squared plus 1.
1 over thing squared plus 1.
Oh yeah.
Okay. Okay.
If you can cope.
Yep.
Otherwise you're good. That's it. So that's 4x over, and I'm just going to leave that alone. There is no reason to expand that out. I'm not touching it. That's it. Done. Dos más.
What do we need? The one that's for the derivative. Okay.
Oh, I should put some implicit derivatives in here. Maybe I should add on to this a bit.
You wrote that one backwards too.
Really?
Oh, he did. You did. I don't know if we can be friends anymore.
Let's see what happens. I just made that up. I'm thinking of what.
You know what happens every time you make it up? Not pretty things.
Hey, usually it works out fine. Okay.
1 over e2y square root of e2y squared.
Okay. So we go 1 over, this is a secant. So we've got the stuff here, right? And then we've got a square root. And which way does it go? 1 minus or a thing minus? So it's thing squared minus 1
Times
I'm just reminding you about your webinar.
times 2.
I'll be right over.
Okay.
Webinar.
Thanks.
What is a webinar?
It's a mix of a
I've got a training.
Caltech has a very nice
Okay,
one.
so
If you
what
wanna
else am I
look at it.
missing?
e2y times 2y prime.
Oh.
Y prime
2y.
plus 16x.
You okay with that? Hello?
No.
Okay.
I need to think for a second. You went so fast.
Okay.
Oh, I got
This is 1 over x. X squared minus 1. That's for the arc secant, right? Then you've got the chain rule. So let's cover everything up except for the thing inside. What's the derivative of that? E to the 2y. Derivative of e to the x, e to the x, right? And then the derivative of that, when I cover that up, is 2y prime.
Oh, just went.
I'm feeling okay.
Yes.
We're feeling the power. Equals. The other side's easy.
Y prime plus 16x?
Yeah. So then how many terms do we have here? Careful.
You can cross out the e to the 2y and
One on that.
Well, we've just got one big term.
yeah, just one big.
And
Cross out eating
2 over there. Now they're both saying this is just really up here. All this stuff is really up here, right? I can just put it up here. So can't I just cross it out? You betcha. That goes away.
So then what do you get?
2
So I'm going to pull this y prime over.
8x squared.
Let's just square this. That's e to the what? Power to power is
4y.
multiply.
Move your y prime over.
Move my y prime over and factor out. I'm going to do it all in one step. So if I pull the y prime out of that, it's 2 over stuff. If I pull the y prime out of that after it's been over, what is it? Minus 1.
Did you hear that?
16
Did you hear what they
x
said?
divided by
wait, did you leave the 16x on that side? I can't see.
Yes.
It's really not that complicated to plug into, though, is it?
If you were to find a common denominator for the bottom, do you think you'd be able to cancel out some stuff?
Maybe. I don't think it would get much cleaner, though.
Yeah.
Good question. Is it a single fraction, though? Yes, and that would be very useful to us. So I actually don't think we need to simplify it most likely for most purposes.
Yeah.
Good idea, though. Should we do one last one that's not implicit? So that's about as hard as one of our derivatives can be, I think. I mean,
You know, I got some really nasty ones when I was trying to solve this without the derivatives from the arc. I got really gross.
okay.
Just be honest.
Okay, Kyle, can you help me start?
He saw you talking to me, so he picked
He
you
saw
up.
you talking to me, actually.
I actually wasn't caring. I just wanted Kyle. Just wanted to hear Kyle.
Can we
Go.
change it to x, please?
Okay, first we'll change the arc sign of t to 1 over the square root of 1 minus t squared.
Excellent. Okay, done with that part, right? Okay, can somebody help him?
I'll take a product.
We have a product rule, so
Oh,
plus
okay.
Plus T.
t
Times
times,
the derivative of
which
square
is
root
going to
of
be
1.
like a half,
Okay, half
1
times
minus t squared to the negative 1/2 times 2t, because of that part.
Wait, what does that say? Minus, okay, thanks.
I'm not color coding, sorry, I got
No,
tired.
no, no, it's okay.
Plus the second thing, the second part's easy. Times 1. Yeah. Now, this I think I can really
You have a
simplify
common
nice, watch.
Denominator.
Oh, yeah, those will count.
You will get
This is t, ooh, stuff cancels, yeah, I see what Brent's saying. Brent's saying that 2 and that 2 cancel.
And then T
1 minus t.
We've got a t squared over, that changes into,
Square root of 1.
look at that, it's the same thing.
Wait, how, where's 0?
Oh.
2 t's.
Yeah.
Yeah.
Okay.
2's are gone. That can get in this. Then we've got plus that thing on top. I think those parts combine real nice.
Wait, because it's raised to the negative 1/2, would you have 2 on the bottom, like t squared over 2 times the square root?
1/2 is square root, and
Oh, okay,
put it
never
on the
mind.
bottom.
All right.
You okay?
Yep.
And on that thing, you can multiply by 1, like root 1 minus t squared over root 1 minus t squared.
Thank you, Mr. Bordino. Mr. Bordino saying, why, it'd be so nice if we just had this over here. Because then what's gonna happen? Watch how simple this is gonna get. Yeah, I'm gonna be right
It's
over.
1 minus t.
So I've got 1 plus t squared,
Plus
and then
1 minus t squared.
So it's
if
2.
you multiply those two things together, you've got 1 minus t squared, don't you? So look at that. That is good stuff. This monstrosity simplified to something so simple. Now, like in the next section, we're going to ask, like, where is the derivative 0? We've even done that a couple times already, right? Like, where is the tangent line horizontal? Well, you guys tell me, where is the tangent line horizontal for y? Where is that fraction equal to 0? It's not, because the top is 2. You don't even look at the bottom, do you? If you want to know where it's 0, is 0 equal to 2? So we just proved that this function has 0 horizontal tangent lines anywhere in reality. Okay. Now, why would we want those kind of things? We're going to start to see in the next chapter for sure. Okay. That was nice. Okay, you guys have the assignment up there.
You?